please settle in. Let the world around you fade for a moment. If you can, expand this to full screen. Let the vastness we're about to explore fill your field of vision completely. And if this journey resonates with you, if the questions we pursue together feel worth preserving, consider subscribing. Not out of urgency, but out of quiet companionship in the search for understanding. Now let us begin. There exists, in the observable universe, a region of space that is colder than it should be. Not colder in the sense of ordinary temperature, not colder as measured by thermometer held to matter, but colder in a far more profound and pervasive way. This cold manifests in the oldest light we can detect, light that has traveled across the entire span of cosmic history to reach us. This light, when examined with extraordinary precision, reveals a pattern of warmth and cold spread across the entire sky. And within that pattern, there is a particular region, a specific zone, where the temperature deviates from expectation in a manner that has compelled some scientists to consider the possibility that it might be evidence, however uncertain and contested, of another universe lying beyond our own. To understand why this idea has emerged, why a simple measurement of temperature in ancient light could lead to such an extraordinary hypothesis, we must begin not with speculation, but with observation. We must build our understanding carefully, step by step, from the most basic empirical facts about the universe we inhabit, the light that fills it, and the methods we have developed to read the messages encoded in that light. The universe is filled with light, not merely the light of stars, which occupies only a tiny fraction of the total luminous energy present in the cosmos, but with a far more diffuse, far more uniform glow that permeates all of space. This glow is not visible to the human eye. It does not illuminate our nights or cast shadows on distant worlds. It exists at wavelengths far longer than those our eyes evolved to detect, wavelengths corresponding not to the colors of the visible spectrum, but to microwave radiation, the same general category of electromagnetic waves used in microwave ovens and certain forms of telecommunications. This microwave glow is called the cosmic microwave background, often abbreviated as CMB. It is the afterglow of the Big Bang, a relic of the earliest epoch of the universe when all matter and energy were compressed into a state of extreme density and temperature. The existence of this background radiation was predicted theoretically in the mid-20th century as a necessary consequence of the Big Bang model, and it was discovered serendipitously in 1964 by Arno Penzias and Robert Wilson, who detected an unexpected uniform noise in their radio antenna that could not be attributed to any terrestrial or astronomical source they could identify. That noise, that faint hiss present in every direction of the sky, was the cosmic microwave background, and its discovery transformed cosmology from a largely speculative discipline into an observational science grounded in concrete measurement. The cosmic microwave background originates from a specific moment in cosmic history, approximately 380,000 years after the Big Bang. Before that moment, the universe was so hot and dense that matter existed not as atoms, but as a plasma, a seething soup of free electrons and atomic nuclei. In such a state, photons, the particles of light, could not travel freely. They were constantly scattered by the free electrons, bouncing from particle to particle in a chaotic dance that prevented them from streaming across space. The universe was opaque, filled with light, but unable to transmit that light over any significant distance. But as the universe expanded, it cooled. Eventually, the temperature dropped to a point where electrons and nuclei could combine to form neutral atoms, primarily hydrogen and helium. This process is called recombination, though the term is somewhat misleading because the electrons and nuclei were not recombining in the sense of reuniting. They were combining for the first time. Once neutral atoms formed, the free electrons that had been scattering photons were no longer free. The photons suddenly found themselves able to travel unimpeded across space. The universe became transparent. The light that had been trapped in the plasma was released, and it has been traveling through space ever since, cooling and stretching as the universe itself expands. Today, that light reaches us from all directions. It has been traveling for more than 13 billion years, and in that time, the expansion of the universe has stretched its wavelength from the visible and infrared range into the microwave range. What was once a searing bath of light with a temperature of roughly 3,000 degrees Kelvin is now a faint glow with a temperature of approximately 2.7 degrees above absolute zero. This temperature, 2.7 Kelvin, is remarkably uniform across the entire sky. If you were to measure the temperature of the cosmic microwave background in one direction, then turn and measure it in the opposite direction, you would find the two measurements to agree to within a few parts in 100,000. This extraordinary uniformity is one of the most important facts about the cosmic microwave background. It tells us that the early universe was remarkably smooth, that the distribution of matter and energy at the moment of recombination was nearly, though not perfectly, homogeneous. If the universe had been perfectly uniform, however, the cosmic microwave background would exhibit exactly the same temperature in every direction, and no structure, no galaxies, no stars, no planets, no observers could have formed. Structure requires variation, seeds of density that can grow under the influence of gravity into the cosmic web of galaxies and voids we observe today. Those seeds are present in the cosmic microwave background as tiny deviations from perfect uniformity. These deviations are called temperature anisotropies, meaning variations in temperature across different directions in the sky. The anisotropies are extremely small, typically on the order of tens of microkelvins, a few millionths of a degree, superimposed on the average temperature of 2.7 Kelvin. To detect them requires instruments of extraordinary sensitivity and precision, instruments capable of measuring temperature differences far smaller than any thermometer in everyday use could resolve. The first detection of these anisotropies came in 1992 from the Webb satellite, the Cosmic Background Explorer, which mapped the temperature of the cosmic microwave background across the entire sky with sufficient precision to reveal the presence of fluctuations. Subsequent missions, particularly the Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, and the Planck satellite, launched in 2009, have mapped these fluctuations with ever-increasing resolution and sensitivity, producing detailed images of the temperature variations across the sky. When these maps are displayed, they show a modeled pattern of warmer and cooler regions, color-coded to emphasize the tiny deviations from the average temperature. Hot spots appear in one color, cool spots in another. The pattern is complex, with variations on many different angular scales, from broad swathes covering large fractions of the sky to small patches only a fraction of a degree across. The statistical properties of this pattern encode a wealth of information about the universe. Its age, its composition, its geometry, the nature of the primordial fluctuations that seeded structure formation, and much more. Cosmologists have learned to extract this information by analyzing the angular power spectrum of the fluctuations, a mathematical tool that quantifies how much variation exists on each angular scale. Within this intricate tapestry of hot and cold, however, there is one region that stands out. It is not the hottest spot, nor the coldest in an absolute sense, but it is unusually cold relative to its surroundings, and it is unusually large. This region is located in the southern sky, in the direction of the constellation Eridanus. It spans an angular diameter of roughly 5 to 10 degrees, depending on how its boundaries are defined, which corresponds to a physical scale of hundreds of millions of light-years across, given the distance to the surface of last scattering, the sphere in space from which the cosmic microwave background photons were emitted. This region has come to be known as the cold spot. It was first noted in the data from the WMAP satellite and was subsequently confirmed and studied in greater detail by the Planck satellite. The cold spot is not an isolated phenomenon in the sense that there are no other cold regions in the cosmic microwave background. There are many. But the combination of its size and the degree of its coldness makes it a statistical outlier. If the temperature fluctuations in the cosmic microwave background were purely random, drawn from a distribution predicted by the standard cosmological model, the probability of finding a cold region of this size and this magnitude would be very low, though not impossible. Quantifying exactly how improbable it is depends on the details of the statistical analysis, on how one defines the boundaries of the feature, on how one accounts for the so-called look elsewhere effect, the fact that when you examine a large dataset you expect to find some rare features simply by chance, but by many estimates, the cold spot is unusual enough to warrant attention. The existence of the cold spot raises a question. What could cause such a feature? There are, in principle, several possibilities. It could be a statistical fluke, a rare, but not impossible fluctuation arising from the random quantum processes that generated the primordial density perturbations in the very early universe. It could be the result of a foreground effect, some structure or process lying between us and the surface of last scattering that imprints an apparent temperature variation on the cosmic microwave background. Or it could be the signature of something more exotic, some physical process or cosmic structure not accounted for in the standard model of cosmology. To evaluate these possibilities, we must deepen our understanding of how the cosmic microwave background acquires its temperature pattern and how intervening structures and processes can modify that pattern. The temperature fluctuations we observe in the cosmic microwave background originate from two primary sources. The first is variations in the density of matter at the moment of recombination. Regions where the density was slightly higher than average would have been slightly hotter, because the gravitational energy associated with denser regions contributed to the temperature of the photons. Conversely, regions of lower density were slightly cooler. These are called intrinsic fluctuations because they were imprinted directly into the radiation field at the moment the photons decoupled from matter. The second source of fluctuations is the effect of the gravitational potential wells and hills present at the surface of last scattering. Photons climbing out of a gravitational potential well lose energy, becoming redshifted and thus cooler, while photons falling into a potential well gain energy, becoming blue-shifted and thus hotter. However, because the universe was expanding and the potential wells themselves were evolving, there is a net effect related to the time evolution of the gravitational potentials that contributes to the observed temperature pattern. This is known as the Sachs-Wolf effect, named after Rainer Sachs and Arthur Wolf, who first described it in 1967. In addition to these effects imprinted at the surface of last scattering, the cosmic microwave background photons can also be affected by structures they encounter during their journey to us. One important such effect is called the integrated Sachs-Wolf effect. As the universe evolves, the gravitational potential wells associated with large-scale structures can change in depth. If a photon passes through a region where the potential well is becoming shallower over time, it will gain a net energy boost because it will have gained more energy falling into the well than it loses climbing out. Conversely, if the potential well is deepening, the photon will lose net energy. In a universe dominated by matter, where the expansion is decelerating, potential wells tend to remain constant or deepen, and the integrated Sachs-Wolf effect is negligible. But in a universe dominated by dark energy, where the expansion is accelerating, as our universe appears to be, potential wells tend to become shallower over time, and the integrated Sachs-Wolf effect becomes significant. This effect is relevant to the cold spot because it offers a potential explanation for an anomalously cold region. If there exists along our line of sight to the surface of last scattering a particularly large and underdense region, a vast void in the cosmic web, a region where the density of galaxies is much lower than average, then photons passing through that void would experience a net loss of energy. They would enter the void when the gravitational potential was relatively deep, climb out as the potential became shallower due to the accelerating expansion, but the net effect would be that they lose energy overall, becoming cooler. This cooling would add to whatever intrinsic temperature the photons had when they left the surface of last scattering, creating an anomalously cold spot in the observed map. This explanation, involving a supervoid along the line of sight, has been one of the primary conventional hypotheses proposed to account for the cold spot. Several observational efforts have been undertaken to search for evidence of such a void. Surveys of galaxies in the direction of the cold spot have indeed found evidence of a region with a lower density of galaxies than average, though the exact properties of this underdense region, its size, depth, and precise alignment with the cold spot, remain subjects of ongoing research and debate. Some studies have found that the observed underdensity is sufficient to explain at least part of the cold spot's anomalous temperature, while others have argued that even the largest voids detected are not sufficient to fully account for the feature, leaving room for additional explanations. The challenge in definitively confirming or ruling out the supervoid explanation lies in the difficulty of measuring the three-dimensional structure of the universe along the specific line of sight corresponding to the cold spot. Galaxies are not uniformly distributed, and mapping the distribution requires painstaking spectroscopic surveys to measure redshifts, which indicate distances. The deeper and more extensive these surveys become, the better we can map the large-scale structure, but our view remains incomplete, especially at the very large scales relevant to the cold spot. Moreover, even if a supervoid is confirmed, the question remains whether it is itself unusual. The universe contains many voids, and while large voids are rarer than small ones, the presence of a large void is not, in itself, surprising. What would be surprising is if the void were so large and so underdense that its existence could not be readily accommodated within the statistical predictions of a standard cosmological model. If the void required to explain the cold spot is exceptionally rare, then explaining the cold spot with a void simply shifts the question from why is there a cold spot to why is there such an unusual void. This is where the more exotic explanations begin to enter the discussion. If the cold spot cannot be fully explained by statistical fluctuation in the primordial density field, and if it cannot be fully explained by foreground structures like supervoids, then we are compelled to consider other possibilities. One such possibility, which has received significant attention in the scientific literature and in popular science discussions, is that the cold spot might be evidence of a collision or interaction between our universe and another universe. To understand how such an idea could even be conceived, we must venture into the realm of theoretical cosmology and explore the concepts of cosmic inflation, the multiverse, and the quantum origins of the universe. The standard Big Bang model, as originally formulated, describes the universe as expanding from an initial state of extreme density and temperature. It successfully explains the expansion of the universe, the cosmic microwave background, and the abundance of light elements like hydrogen and helium. However, it does not explain why the universe is so uniform on large scales, why it is so flat in its geometry, or what generated the primordial density fluctuations that seeded structure formation. These are known as the horizon problem, the flatness problem, and the origin of structure, respectively. In the early 1980s, a modification to the Big Bang model was proposed to address these issues. This modification is called cosmic inflation. Inflation posits that the universe underwent a brief period of extraordinarily rapid expansion in the first fraction of a second after the Big Bang, driven by a form of energy associated with a quantum field, often called the inflating field. During this inflationary epoch, the universe expanded exponentially, doubling in size many times over in an extremely short interval. This rapid expansion stretched the universe to enormous size, smoothing out any initial irregularities and flattening its geometry. It also stretched quantum fluctuations in the inflating field and other fields to macroscopic scales. And these fluctuations, once inflation ended and the energy of the inflating field was converted into matter and radiation, became the seeds of the density fluctuations we observe in the cosmic microwave background. Inflation is an extraordinarily successful framework. It explains the uniformity and flatness of the universe, and it provides a mechanism for generating the primordial fluctuations with precisely the properties observed in the cosmic microwave background. However, inflation also has profound and somewhat unsettling implications when taken to its logical conclusions. If inflation occurred in our universe, driven by an inflating field with certain properties, then it is natural to ask whether inflation occurred elsewhere in other regions of space, and whether it might still be occurring in some regions even now. In many versions of inflationary theory, particularly those involving certain types of inflating potentials, inflation does not end everywhere at once. Instead, it ends in some regions while continuing in others. The regions where inflation ends become universes like ours, filled with matter and radiation, expanding and cooling. The regions where inflation continues keep expanding exponentially, and within those regions, inflation will eventually end in some subregions, creating more universes, while continuing in others. This process can repeat indefinitely, leading to a vast, ever-growing ensemble of universes, each potentially with different properties, different physical constants, different numbers of dimensions, different forces and particles. This ensemble is called the multiverse, or more specifically, the inflationary multiverse. In the context of the multiverse, our observable universe is just one bubble among countless others, each bubble representing a region where inflation ended. These bubbles are separated from one another by regions of space that are still inflating. However, if two such bubbles form close enough to one another in the inflating background, there is a possibility that they could collide. The collision would occur when the expanding boundaries of the two bubbles meet. What would such a collision look like? This is a question that theoretical physicists have explored through detailed calculations and computer simulations. The answer depends on the specifics of the inflationary model, the properties of the bubbles, and the dynamics of the collision, but the general picture is as follows. When two bubble universes collide, the collision would release energy at the boundary where they meet. This energy would propagate into each bubble, creating a disturbance. From the perspective of an observer inside one of the bubbles, the collision would appear as a signal arriving from a specific direction in space. The signal would affect the cosmic microwave background, imprinting a distinctive pattern on the temperature fluctuations. The exact pattern depends on the details, but in many scenarios, the collision would create a disk-like feature in the sky, a region where the temperature of the cosmic microwave background is either hotter or colder than average, with a degree of temperature variation potentially varying with angular distance from the center of the disk. This is where the cold spot re-enters the discussion. If the cold spot is the result of a collision with another universe, then it would represent the imprint of that collision on our cosmic microwave background. The coldness of the spot could result from the specific dynamics of the collision, from the way energy was transferred or not transferred between the two bubbles, from the relative phases of the inflating fields, or from other details of the collision physics. This hypothesis is extraordinary, and extraordinary claims require extraordinary evidence. The question becomes, does the cold spot exhibit the specific features that would be expected from a bubble collision, as opposed to other explanations like a supervoid or a statistical fluctuation? Several studies have attempted to address this question. Some have analyzed the shape and temperature profile of the cold spot to see if it matches the predictions of bubble collision models. The results have been mixed. Some analyses suggest that the cold spot is consistent with certain collision scenarios, while others argue that the feature does not exhibit the precise symmetry or profile expected from a collision, or that the likelihood of a collision producing exactly the observed feature is not significantly higher than the likelihood of the feature arising from conventional processes. One challenge in this analysis is that the theoretical predictions for bubble collisions are not unique. Different inflationary models, different collision geometries, different timings of the collision relative to the end of inflation in our bubble all lead to different observational signatures. There's not a single sharp prediction that can be tested. Instead, there's a range of possible signals, and the question is whether the observed cold spot falls within that range in a way that is more natural or more probable than the conventional explanations. Another challenge is the inherent difficulty in distinguishing between different sources of large-scale anomalies in the cosmic microwave background. The cosmic microwave background is a single realization of a random field. We have only one universe to observe, one sky to map. Statistical inference from a single realization is inherently limited. If we could observe many universes or many independent patches of sky large enough to contain features like the cold spot, we could assess how often such features arise by chance. But we cannot. We must make do with statistical models and simulations, which themselves depend on assumptions about the underlying cosmological model. Despite these challenges, the bubble collision hypothesis remains a tantalizing possibility. It represents a way in which a feature in our observable universe could carry information about a reality far beyond what we can directly observe, a reality in which our universe is just one among many, and in which those many universes can interact in observable ways. To fully appreciate the significance of this hypothesis and the reasons why it is taken seriously by at least some scientists despite its speculative nature, we must deepen our understanding of the multiverse concept itself, its theoretical motivations, and the extent to which it is grounded in established physics versus more speculative extensions. The multiverse is not a single, well-defined theory, but rather a consequence of several different theoretical frameworks in modern physics. The inflationary multiverse, which we have already discussed, is one version. But there are others, each arising from different aspects of fundamental physics. One version is the quantum multiverse, or many-worlds interpretation of quantum mechanics. According to quantum mechanics, the state of a physical system is described by a wave function, and the wave function evolves deterministically according to the Schrödinger equation. However, when a measurement is made, the wave function appears to collapse, yielding a single definite outcome from among the many possibilities encoded in the wave function. The Copenhagen interpretation of quantum mechanics treats this collapse as a fundamental process, but does not explain what causes it or how a definite outcome is selected. The many-worlds interpretation, proposed by Hugh Everett in 1957, offers a different perspective. It suggests that the wave function never collapses. Instead, all possible outcomes of a measurement actually occur, each in a different branch of reality. The universe splits, or more accurately, is constantly branching into a vast number of parallel worlds, each representing a different sequence of measurement outcomes. In this view, there is no single, definite reality, but rather a superposition of all possible realities, all equally real, though mutually inaccessible to observers within any one branch. While the many-worlds interpretation is philosophically striking, it does not directly predict observable consequences like the cold spot. The branches of the quantum multiverse are causally disconnected. They do not interact once they split. Thus, evidence for the many-worlds interpretation cannot come from observing collisions or interactions between branches. Another version of the multiverse arises from string theory, a theoretical framework that attempts to unify all the fundamental forces of nature, including gravity, within a single consistent quantum theory. String theory requires extra spatial dimensions beyond the three we experience. These extra dimensions must be compactified, curled up into tiny shapes too small to observe directly. The specific way in which the extra dimensions are compactified determines the properties of the particles and forces in the resulting four-dimensional world. There are an enormous number of possible compactifications, often estimated to be on the order of 10 to the 500 or more, each corresponding to a different possible set of physical laws. This vast collection of possibilities is sometimes called the string theory landscape. If different regions of space, perhaps regions that inflated and formed separate bubbles, underwent different compactifications, then each bubble would have different physical properties, different particle masses, different force strengths, different cosmological constants. This is another form of multiverse, the landscape multiverse, where the diversity arises not from different branching histories, but from different vacuum states of the underlying theory. The inflationary multiverse and the landscape multiverse can be combined. If inflation is eternal, constantly creating new bubbles, and if each bubble can settle into a different vacuum state from the string theory landscape, then the resulting multiverse would contain an enormous diversity of universes, each with potentially wildly different properties. Most of these universes would be uninhabitable, devoid of the specific conditions necessary for the formation of stars, planets, and life. But in such a vast ensemble, some universes would, by chance, have properties compatible with the emergence of complexity in observers. We would necessarily find ourselves in one of those rare, habitable universes not because our universe is special in any fundamental sense, but simply because only in such a universe could observers exist to ask the question. This is an application of the anthropic principle, the idea that our observations of the universe are necessarily biased by the requirement that conditions must be suitable for our existence. The multiverse, in any of its forms, is a controversial concept in physics. Some scientists embrace it as a natural and perhaps inevitable consequence of our best theories of cosmology and quantum gravity. Others reject it as untestable and therefore unscientific, arguing that a theory that predicts the existence of entities that cannot be observed, even in principle, is not a scientific theory but a metaphysical speculation. The debate is ongoing and deeply entwined with questions about the nature of scientific explanation, the role of testability in theory evaluation, and the limits of empirical inquiry. However, the bubble collision hypothesis offers a potential way to make the multiverse testable, at least in principle. If other universes exist, and if they can collide with ours, then those collisions could leave observable imprints on the cosmic microwave background. The cold spot is one candidate for such an imprint. If it could be definitively shown that the cold spot is best explained by a bubble collision, and if that explanation could be embedded within a well-defined theoretical framework that makes additional testable predictions, then we would have empirical evidence for the multiverse. We would have moved from pure speculation to observation-grounded inference. This possibility, remote as it may be, is what lends the cold spot its extraordinary allure. It is not merely an unexplained feature in a dataset. It is a potential window into a reality far vaster and stranger than the universe we can see, a reality in which our cosmos is just one bubble in an infinite, ever-growing foam of universes. To assess whether the cold spot truly represents such a window, we must examine the observational evidence in greater detail, exploring not only the cold spot itself, but also other anomalies in the cosmic microwave background and the extent to which they cohere into a pattern that might suggest physics beyond the standard model. The cosmic microwave background, despite its overall agreement with the predictions of the standard cosmological model, exhibits several anomalies that have puzzled cosmologists. The cold spot is one of the most prominent, but it is not alone. There are others, sometimes collectively referred to as the axis of evil, and related large-scale anomalies. One such anomaly involves the alignment of the lowest multipole moments in the angular power spectrum of the cosmic microwave background. The angular power spectrum is a way of decomposing the temperature fluctuations into contributions from different angular scales. The lowest multipoles correspond to the largest angular scales, the broadest features in the sky. In a universe that is statistically isotropic, meaning it has no preferred directions, these low multipoles should be randomly oriented with respect to one another. However, analyses of the WMAP and Planck data have suggested that the quadrupole and octupole moments, the second and third lowest multipoles, are unexpectedly aligned with each other and also seem to have a preferred orientation with respect to the geometry of the solar system and the plane of the galaxy. This alignment is surprising and difficult to explain within the standard model. It could be a statistical fluke, or it could indicate some unrecognized systematic error in the data analysis, or it could be a sign of new physics. Another anomaly is the so-called hemispherical asymmetry. The cosmic microwave background appears to be slightly colder in one hemisphere of the sky and slightly warmer in the opposite hemisphere. The difference is small, but it is statistically significant. This asymmetry suggests a violation of the assumption of statistical isotropy, the idea that the universe should look the same on average in all directions. Again, this could be a statistical accident, a subtle instrumental effect, or a genuine feature of the universe requiring explanation. These anomalies, taken together, suggest that the universe might not be as simple or as perfectly described by the standard model as we would like. They leave room for the possibility that there are additional physical processes, perhaps acting on very large scales, that are not captured in the current framework. Bubble collisions with other universes are one possible such process, but there are others. Some have proposed that the anomalies could be explained by a non-trivial topology of the universe, meaning that the universe might be finite and have a specific shape that causes correlations in the cosmic microwave background on large scales. Others have suggested that the anomalies could arise from modifications to the inflationary model or from the effects of cosmic strings or other topological defects left over from phase transitions in the early universe. The scientific process of evaluating these possibilities involves developing detailed theoretical models, making predictions for what those models would imply for the statistical properties of the cosmic microwave background, and then comparing those predictions with the data. This process is painstaking and requires careful attention to statistical methodology, to the treatment of systematic uncertainties, and to the risk of confirmation bias, the tendency to favor interpretations that align with one's expectations or preferences. In the case of the cold spot and the bubble collision hypothesis, several groups of researchers have performed analyses aimed at testing whether the observed feature is consistent with the predictions of collision models. One approach is to simulate what the cosmic microwave background would look like if a bubble collision had occurred, varying the parameters of the collision, such as the angle of impact, the time at which the collision occurred relative to recombination, the energy released in the collision, and the properties of the inflating field. These simulations produce a range of possible temperature patterns. The next step is to compare these simulated patterns with the observed cold spot, using statistical measures to quantify how similar they are. Some studies have found that certain bubble collision scenarios can produce features similar to the cold spot, and that the goodness of fit is comparable to or slightly better than the fit obtained with conventional explanations like a supervoid. However, these studies also emphasize that the parameter space of collision models is large, and that the improvement in fit is not sufficient to definitively rule out the conventional explanations or to claim a detection of a bubble collision. Other studies have been more skeptical, arguing that the cold spot does not exhibit the specific azimuthal symmetry, the circular shape, that would be expected if it were the result of a collision viewed from our position within the bubble. The debate is further complicated by the fact that the theoretical predictions themselves are uncertain. The physics of bubble collisions is not fully understood. It involves general relativity, quantum field theory in curved spacetime, and the dynamics of phase transitions in the inflating field, all in a regime where our theoretical tools are stretched to their limits. Different assumptions about the details of the collision dynamics can lead to different predictions for the observable signature. Moreover, the probability of a collision occurring, the expected number of collisions we might see in our sky, and the typical properties of those collisions all depend on the specifics of the inflationary model, about which we have limited direct observational constraints. Given these uncertainties, the current status of the bubble collision hypothesis is one of intriguing possibility rather than established fact. The cold spot remains an anomaly, a feature that is not easily explained within the simplest version of the standard cosmological model, and that invites continued investigation. The bubble collision hypothesis offers one potential explanation, one that would have profound implications for our understanding of the universe and our place within a larger multiverse. But it is not the only explanation, and it has not been confirmed to the level of certainty required to overturn the conventional framework. To move forward, what is needed is more data and more refined analysis. Future observations of the cosmic microwave background, with even higher resolution and sensitivity, could reveal additional features or provide better constraints on the properties of the cold spot. Deeper surveys of the galaxy distribution in the direction of the cold spot could better map the three-dimensional structure along the line of sight and test the supervoid hypothesis more rigorously. And continued theoretical work could refine the predictions of bubble collision models, making them more specific and more testable. But even if the bubble collision hypothesis is ultimately ruled out as the explanation for the cold spot, the questions it raises will remain. The cold spot and the other anomalies in the cosmic microwave background remind us that our understanding of the universe is incomplete. They push us to consider possibilities beyond the standard model, to question our assumptions, and to search for new physics that might operate on the largest scales. This search is not driven by a desire to overturn established science for its own sake, but by the recognition that science progresses through the confrontation of theory with observation. When observations reveal unexpected features, when the data does not quite fit the predictions, that is when opportunities for discovery arise. The history of physics is filled with examples where small anomalies, initially dismissed or explained away, eventually led to major breakthroughs. The anomalous precession of Mercury's orbit leading to general relativity, the unexpected results of the Michelson-Morley experiment leading to special relativity, the anomalous rotation curves of galaxies leading to the discovery of dark matter. It is possible, though by no means certain, that the cold spot and related anomalies in the cosmic microwave background will one day be seen as the first hints of a new understanding of the cosmos. To appreciate the full depth of what is at stake, we must return to the fundamental question of what the cosmic microwave background actually is and what it tells us about the nature of reality. The cosmic microwave background is often described as a snapshot of the universe at a specific moment in time, the moment of recombination. This description is useful but incomplete. What we observe when we map the cosmic microwave background is not a photograph of matter at a single instant, but rather a pattern of light, a pattern encoded in the wavelengths and directions of photons reaching us now, after traveling across the universe for more than 13 billion years. Each photon carries information about the conditions at the point in space and time where it last interacted with matter, which for the cosmic microwave background photons is the surface of last scattering. But the information is not direct or simple. It is mediated by the journey the photon has taken, by the gravitational fields it has traversed, by the expansion of space that has stretched its wavelength, and by the quantum fluctuations that were present at the moment of its origin. To decode this information, to extract from the pattern of photons a reliable picture of the early universe and the processes that shaped it, requires both sophisticated observational techniques and a deep theoretical framework. The observational techniques involve building detectors sensitive to microwave radiation, placing those detectors in locations where terrestrial interference is minimized, such as high-altitude balloons, remote deserts, or space, and carefully calibrating the instruments to remove sources of systematic error. The detectors must measure not only the intensity of the radiation, but also its polarization, because the cosmic microwave background is partially polarized, and the pattern of polarization contains additional information about the early universe, particularly about gravitational waves produced during inflation and about the process of reionization, when the first stars and galaxies formed and began to ionize the surrounding hydrogen. The theoretical framework involves modeling the evolution of the universe from the earliest moments after the Big Bang through the present day, calculating how density fluctuations grow under the influence of gravity, how photons scatter off free electrons and protons, how gravitational potentials evolve as the universe expands, and its composition changes from radiation-dominated to matter-dominated to dark energy-dominated. These calculations are implemented in sophisticated computer codes that take as input the parameters of the cosmological model, such as the density of ordinary matter, the density of dark matter, the density of dark energy, the rate of expansion, the amplitude and spectral index of the primordial fluctuations, and so on, and produce as output the predicted statistical properties of the cosmic microwave background, particularly the angular power spectrum and the polarization spectrum. By comparing the predicted spectra with the observed spectra, cosmologists can constrain the values of the cosmological parameters. This process has been remarkably successful. The measurements from WMAP and Planck have determined the parameters of the standard cosmological model with percent-level precision, confirming that the universe is spatially flat, that it is approximately 13.8 billion years old, that it is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, and that the primordial fluctuations have very nearly a scale-invariant spectrum, as predicted by the simplest models of inflation. This success is one of the great triumphs of modern cosmology. It demonstrates that we can use observations of the cosmic microwave background to learn about the universe on the largest scales and at the earliest times accessible to observation. But it also makes the anomalies, like the cold spot, all the more intriguing. If the standard model works so well overall, why does it seem to fail, or at least strain, in explaining certain specific features? One possible answer is that we are overinterpreting the anomalies. Statistical fluctuations are expected, and in a sufficiently large dataset, rare events will occur. The cosmic microwave background contains a finite number of independent modes, and when we search through the data for unusual features, we are effectively performing many statistical tests. Some of those tests will produce apparently significant results by chance. This is the look elsewhere effect, and it is a serious concern in any analysis that involves searching for anomalies in large datasets. Proper statistical methodology requires accounting for this effect, typically by adjusting significance levels or by performing simulations to determine how often features like the ones observed would arise by chance in datasets generated from the standard model. When such corrections are applied, the statistical significance of the cold spot and other anomalies is reduced, though not necessarily eliminated. The cold spot remains unusual, but it is not so unusual that we can confidently rule out chance as an explanation. This is the frustrating and fascinating nature of the problem. The evidence is suggestive but not conclusive, intriguing but not definitive. Another possible answer is that the anomalies are real, but their explanation lies not in exotic new physics, but in subtle effects that are not yet fully incorporated into the standard model. For example, the effect of gravitational lensing by large-scale structure on the cosmic microwave background, which distorts the pattern of fluctuations in a particular way, is a known effect that has been detected and measured, but the full impact of lensing on the statistical properties of the cosmic microwave background, especially on large scales, is still an area of active research. Similarly, the effect of the motion of the solar system relative to the cosmic microwave background rest frame, which creates a dipole anisotropy, is well understood and routinely subtracted from the data, but there could be more subtle kinematic effects or effects related to the local environment of our galaxy that have not been fully accounted for. Yet another possibility, the one that has motivated this extended exploration, is that the anomalies are indeed signs of new physics, and that among the possible new physical processes, bubble collisions represent one candidate. This possibility remains speculative, but it is grounded in theoretical frameworks, particularly eternal inflation and the multiverse, that are themselves grounded in extensions of well-established physics. Whether these frameworks ultimately prove correct, whether they make testable predictions, and whether those predictions are borne out by observation, are questions that future research will address. In the meantime, the cold spot stands as a marker, a specific feature in the sky that concentrates our attention and challenges our understanding. It is located at particular coordinates in the constellation Eridanus, and it can be pointed to, mapped, studied with increasing precision. It is not merely an abstract theoretical puzzle, but a concrete observational fact, a cold region in the cosmic microwave background that demands explanation. To understand why this coldness is so significant, why a temperature deficit of a few tens of microkelvins spread over several degrees of the sky could be considered potential evidence for another universe, we must delve more deeply into the nature of temperature itself in the context of the cosmic microwave background, and into the mechanisms by which temperature variations can be imprinted and modified. Temperature, in everyday experience, is a measure of the average kinetic energy of the particles that make up a substance. The hotter something is, the faster its constituent atoms or molecules are moving. In the context of the cosmic microwave background, temperature refers to the spectrum of the radiation, specifically to the fact that the radiation has a blackbody spectrum, a specific distribution of intensity versus wavelength that is characteristic of thermal equilibrium. A perfect blackbody spectrum is determined by a single parameter, the temperature. For the cosmic microwave background, the average temperature is 2.725 Kelvin, meaning that the spectrum of the radiation matches that of a perfect blackbody at that temperature to extraordinary precision. The temperature variations we observe in the cosmic microwave background are deviations from this average. In one direction, the temperature might be 2.72501 Kelvin. In another direction, 2.72499 Kelvin. These tiny differences, just a few hundred thousandths of a degree, are what we call the temperature anisotropies. They arise because different regions of the surface of last scattering had slightly different temperatures, slightly different densities, and slightly different velocities at the moment of recombination. The temperature anisotropies can be decomposed into different physical contributions. One contribution comes from variations in the intrinsic temperature of the plasma at recombination, which in turn reflects variations in the density. Another contribution comes from the Doppler effect, due to the motion of the plasma. Regions of the plasma that were moving toward us at recombination imprinted a slight blue shift on the photons, making them slightly hotter, while regions moving away imprinted a red shift, making them slightly cooler. Yet another contribution comes from the gravitational redshift associated with climbing out of or falling into potential wells, the Sachs-Wolf effect mentioned earlier. All of these contributions are related to the primordial density fluctuations generated during inflation. Inflation predicts that these fluctuations should be Gaussian, meaning that their statistical distribution is a normal bell curve distribution. Gaussian fluctuations have the property that they are completely characterized by their power spectrum, the amount of variation on each scale, and by higher-order statistics, such as the bispectrum and trispectrum, which quantify correlations between different scales, are predicted to be negligibly small for Gaussian fluctuations. The observed cosmic microwave background is, to very high precision, consistent with being a Gaussian random field. This is a powerful confirmation of the inflationary paradigm. However, if the fluctuations are Gaussian, then the probability of finding a region as cold as the cold spot can be calculated from the power spectrum. This calculation involves integrating the power spectrum to determine the variance of temperature fluctuations on the angular scale of the cold spot, and then using the Gaussian distribution to calculate the probability that a fluctuation of the observed magnitude would occur. As mentioned earlier, this probability is low, though not vanishingly so. The cold spot is a rare, but not impossible fluctuation if the fluctuations are truly Gaussian. But what if the fluctuations are not perfectly Gaussian? What if there is a small amount of non-Gaussianity, meaning deviations from the normal distribution? Non-Gaussianity can arise from various physical processes. For example, if the inflaton field had a non-standard potential, or if there were interactions between the inflaton and other fields, or if there were secondary effects during reionization or from gravitational lensing. These could introduce non-Gaussian features. Additionally, a bubble collision would introduce non-Gaussianity because it would add a localized, non-random signal to the otherwise random temperature field. Detecting non-Gaussianity is a major goal of cosmic microwave background research. The Planck satellite has placed stringent limits on the amount of non-Gaussianity present, finding that the data are consistent with Gaussianity to within a few parts per million in certain statistical measures. These limits are tight enough to rule out many exotic models, but they do not entirely eliminate the possibility of small, localized non-Gaussian features like those that might be produced by a bubble collision. To test whether the cold spot is a non-Gaussian feature, one approach is to perform a Bayesian analysis, comparing the likelihood that the observed data, including the cold spot, arose from a Gaussian random field versus the likelihood that it arose from a Gaussian field plus a bubble collision signal. This requires constructing a detailed model of what a bubble collision signal would look like, including its spatial profile and its statistical properties, and then using Bayesian inference to compute the relative probabilities of the two hypotheses given the data. Such analyses have been performed, and the results, as mentioned earlier, are inconclusive. The data do not strongly favor the collision hypothesis over the Gaussian hypothesis, but they also do not definitively rule it out. This inconclusiveness reflects the fundamental challenge of inferring rare or exotic events from a single observation. If we could observe many independent realizations of the cosmic microwave background, many independent universes, or many independent patches of sky, so large that they are statistically independent, we could assess the frequency of features like the cold spot. But we cannot. We are stuck with one realization, and from that single realization, We must infer both the statistical properties of the underlying process and the probability that any given feature is unusual. This limitation is not unique to cosmology. It arises in any field where the object of study is unique or where repetitions of the experiment are impossible. Historical sciences, such as geology and evolutionary biology, face similar challenges. The Earth's geological history is a single realization of a random process, and from that single realization, geologists must infer the mechanisms and probabilities of various events. Similarly, the evolutionary history of life on Earth is a single realization, and from that single realization, biologists must infer the laws of evolution and the probabilities of various outcomes. In cosmology, this challenge is particularly acute because the object of study is the entire observable universe. We cannot step outside the universe to gain a different perspective, and we cannot observe other universes except, possibly, through indirect effects like bubble collisions. This is why the bubble collision hypothesis is so important. If confirmed, it will provide a rare window into the multiverse, a way of observing, if only indirectly, other universes and their properties. But even if the bubble collision hypothesis is not confirmed, the cold spot will continue to serve as a stimulus for research and a reminder of the limits and possibilities of cosmological inference. It exemplifies the way in which science operates at the boundary of the known and the unknown, using the tools of observation, theory, and statistical reasoning to push that boundary outward, even when the answers remain uncertain. To fully explore the implications of the cold spot, we must also consider what it would mean for our understanding of the universe if the bubble collision hypothesis were confirmed. What would it tell us about the nature of reality, about the structure of the cosmos beyond our observable horizon, and about the processes that brought our universe into being? If the cold spot is the result of a collision with another universe, it would confirm that our universe is indeed part of a multiverse, that there are other regions of space, other bubbles, that have undergone their own inflationary epochs, and that are, in some sense, separate universes with their own histories and properties. This confirmation would be a profound shift in our cosmological worldview. For centuries, the universe has been synonymous with everything that exists, the totality of space, time, matter, and energy. The idea of a multiverse challenges this equivalence, suggesting that the universe we observe is just one component of a larger structure. Moreover, the collision would provide information about the nature of the multiverse. The fact that a collision occurred implies that the other universe is not infinitely far away, that the boundaries of our bubble and the other bubble were close enough to meet. This proximity places constraints on the rate of bubble nucleation, the process by which new bubbles form in the inflating background. If bubbles form too rarely, the typical distance between bubbles would be so large that collisions would be extraordinarily improbable. If bubbles form too frequently, the inflating background would be completely filled with bubbles, leaving no room for further inflation, which would conflict with the idea of eternal inflation. The observation of a collision, if confirmed, would thus provide a direct empirical constraint on the dynamics of eternal inflation. Furthermore, the properties of the collision signal, such as its temperature profile, its size, and any associated features like rings or other structures, could provide information about the physics of the collision itself. This could include information about the energy scales involved, the nature of the inflating field, the properties of the bubble walls, and the way energy is released or absorbed during the collision. Such information would be invaluable for testing and refining theoretical models of inflation and the multiverse. The collision might also provide information about the properties of the other universe. Depending on the details of the collision dynamics, it might be possible to infer whether the other universe had the same vacuum state as ours, the same physical constants, or whether it was significantly different. If the other universe had a different vacuum state, a different value of the cosmological constant, or different particle masses, this could affect the collision dynamics in observable ways. In principle, by studying the collision signal in detail, we might be able to learn something about the physical laws in another universe, a remarkable prospect that underscores the scientific potential of the multiverse hypothesis. However, all of these possibilities depend critically on the confirmation of the bubble collision hypothesis, which, as we have seen, remains uncertain. The current evidence is suggestive but not definitive, and there are plausible alternative explanations for the cold spot that do not invoke collisions with other universes. The supervoid explanation, in particular, remains a viable conventional hypothesis, and continued observational efforts to map the distribution of galaxies along the line of sight to the cold spot will be crucial in testing this hypothesis. In addition to mapping the galaxy distribution, there are other observational strategies that could shed light on the nature of the cold spot. One approach is to search for other potential collision signatures elsewhere in the sky. If bubble collisions are a real phenomenon, and if they occur with some finite probability, then we might expect to find not just one, but several such features in the cosmic microwave background. Systematic searches for disk-like features or other unusual patterns have been conducted, and some candidate features have been identified, but none have been confirmed as collision signals to a level of confidence that would be considered definitive. The challenge is that the expected number of collisions visible in our sky depends on the details of the inflationary model, and for many models, the expected number could be less than 1, making the absence of clear additional signals not particularly informative. Another approach is to look for correlated signals in other observables. For example, if a bubble collision affected the cosmic microwave background, it might also have affected the distribution of galaxies or the properties of the intergalactic medium in the same region of the sky. If such correlations could be detected, they would strengthen the case for a collision. Conversely, the absence of expected correlations could argue against the collision hypothesis or constrain the properties of the collision. Polarization measurements of the cosmic microwave background also hold promise. The collision signal might have a distinctive polarization signature, because the collision would not only affect the temperature, but also the way photons scatter and the resulting polarization pattern. Planck measured the polarization of the cosmic microwave background, but future experiments, with higher sensitivity and resolution, might be able to detect subtle polarization features associated with the cold spot that could help discriminate between different explanations. Looking further ahead, the next generation of cosmic microwave background experiments, including ground-based telescopes like the Simons Observatory and the CMB S4 project, as well as potential future space missions, will provide even more detailed maps of the temperature and polarization of the cosmic microwave background. These observations will improve our ability to characterize the cold spot and other anomalies, to test the supervoid hypothesis, and to search for evidence of bubble collisions or other exotic phenomena. At the same time, advances in theoretical modeling and computational techniques will enable more accurate predictions of the signatures of bubble collisions and other non-standard effects. As our theoretical understanding deepens and our observational capabilities expand, the question of whether the cold spot is evidence of another universe will become increasingly well-defined and increasingly testable. But even as we work toward resolving this question, it is important to recognize the broader context in which it sits. The cold spot is not an isolated puzzle, but part of a larger effort to understand the universe on the largest scales and to test the limits of our cosmological models. This effort encompasses many different lines of inquiry. The measurement of the Hubble constant, the rate of expansion of the universe, which has recently yielded conflicting results from different methods, the study of dark matter, whose nature remains one of the great unsolved problems in physics, the study of dark energy, the mysterious component that makes up the majority of the universe's energy density and drives the accelerated expansion, and the search for signatures of cosmic inflation, including primordial gravitational waves that would leave a distinctive imprint on the polarization of the cosmic microwave background. All of these inquiries are interconnected, and progress in one area often informs and constrains progress in others. The cold spot, and the possibility that it might be evidence of a bubble collision, sits at the intersection of observational cosmology, theoretical physics, and the philosophy of science, raising questions about the nature of evidence, the scope of testable science, and the limits of what we can know about the universe. In considering these questions, we are led to reflect on the nature of cosmology as a science. Cosmology is unique among the sciences in that its object of study, the universe, is not a system we can manipulate or experiment upon in the traditional sense. We cannot create universes in the laboratory, we cannot rerun cosmic history, and we cannot observe the universe from outside. We are embedded within the system we seek to understand, and our observations are limited to a finite region of space and time, the observable universe, bounded by the speed of light and the finite age of the cosmos. Within these constraints, cosmology has nonetheless achieved remarkable success. It has developed a coherent quantitative framework, the standard cosmological model, that account for a vast range of observations, from the expansion of the universe to the cosmic microwave background to the abundance of light elements to the large-scale structure of galaxies. This framework is grounded in well-tested physical theories, general relativity and quantum field theory, and it makes precise predictions that have been confirmed by observation. Yet the framework also has gaps and puzzles. Dark matter and dark energy are included in the model as essential components, but their fundamental nature is unknown. They are inferred from their gravitational effects, but they have not been directly detected or explained within the standard model of particle physics. Cosmic inflation is a highly successful paradigm for explaining the large-scale properties of the universe. But the inflating field, the hypothetical field that drives inflation, has not been identified, and there are many different models of inflation with different predictions. And the anomalies in the cosmic microwave background, including the cold spot, suggest that there may be aspects of the universe that are not fully captured by the simplest version of the standard model. These gaps and puzzles are not signs of failure, but rather opportunities for discovery. They're the places where new physics might emerge, where our understanding might deepen in unexpected ways. The cold spot in this light is not an embarrassment or an anomaly to be explained away, but a feature to be studied, a potential clue to something deeper. To fully appreciate the scientific process by which such clues are pursued, we must consider the interplay between theory and observation, between prediction and measurement, and between hypothesis and test. Science does not progress by pure induction, by simply collecting data and extracting patterns, nor does it progress by pure deduction, by simply deriving predictions from established theories. Rather, it proceeds through a complex feedback loop in which observations motivate the development of theories. Theories make predictions that are tested by further observations, and discrepancies between prediction and observation motivate revisions to the theories or the design of new experiments. In the case of the cold spot, the process began with the observation of an unusual feature in the cosmic microwave background data. This observation prompted questions. Is this feature real, or is it an artifact of the data analysis? If it is real, is it a statistical fluctuation, or does it have a physical cause? If it has a physical cause, what might that cause be? These questions led to theoretical work, developing models that could explain the feature, including the supervoid model and the bubble collision model. Each model makes predictions about the properties of the cold spot and about correlated observables, such as the distribution of galaxies along the line of sight. These predictions are then tested against further observations, and the results inform the evaluation of the models. This process is ongoing. As of the current state of knowledge, the cold spot remains an open question. It is consistent with being a rare statistical fluctuation, it is consistent with being caused by a supervoid, and it is consistent with being caused by a bubble collision. None of these explanations has been definitively confirmed or ruled out. The scientific community continues to gather data, refine models, and perform analyses, slowly narrowing the range of possibilities and moving toward a resolution. This state of uncertainty is, in some ways, uncomfortable. We would like to have definitive answers, to know with certainty what the cold spot is and what it means. But science, especially at the frontiers of knowledge, often operates in a state of uncertainty. Hypotheses are entertained, evidence is weighed, and conclusions are provisional, subject to revision in light of new data or new insights. This tentativeness is not a weakness, but a strength, a reflection of the commitment to empirical grounding and logical rigor that defines the scientific enterprise. The cold spot also illustrates the importance of statistical reasoning in modern science. Much of contemporary physics, from quantum mechanics to cosmology, is fundamentally statistical. We do not predict individual outcomes with certainty, but rather probabilities of different outcomes. The cosmic microwave background is a random field, and our observations are a single realization of that field. To interpret those observations, we must reason probabilistically, using statistical models to infer the underlying processes and to assess the likelihood of different hypotheses. Statistical reasoning, however, is subtle and requires care. It is easy to make errors, to misinterpret significance levels, to fail to account for multiple testing, to overfit models to data, or to be misled by confirmation bias. The scientific community has developed rigorous standards and methodologies to guard against these errors, including peer review, replication, and the use of standardized statistical techniques. But even with these safeguards, statistical inference remains challenging, especially in cosmology, where the data are limited and the models are complex. The cold spot, as a statistical outlier, is particularly challenging to interpret. Is it an outlier because it is a rare but expected fluctuation, or because it is the signature of a genuine deviation from the standard model? How rare does a feature have to be before we conclude that it is not a fluctuation? There is no sharp threshold. Statistical significance is a matter of degree, and the interpretation of significance depends on the context, on the prior probabilities assigned to different hypotheses, and on the costs and benefits of different types of errors. In the case of the cold spot, the prior probability assigned to the bubble collision hypothesis depends on one's assessment of the multiverse framework. If one takes the multiverse seriously as a consequence of well-motivated theoretical frameworks like eternal inflation, then the prior probability might be relatively high, and the cold spot, even as a marginal outlier, might be seen as evidence in favor of the hypothesis. If, on the other hand, one is skeptical of the multiverse, viewing it as speculative and untestable, then the prior probability might be very low, and the cold spot will be dismissed as a likely fluctuation, not warranting further consideration of exotic explanations. This dependence of interpretation on prior beliefs is an inescapable feature of Bayesian reasoning, the framework that underlies much of modern statistical inference. Bayesian reasoning combines prior probabilities, which represent our beliefs or degrees of confidence before seeing the data, with likelihoods, which represent how probable the data are under different hypotheses, to produce posterior probabilities, which represent our updated beliefs after seeing the data. The process is logically consistent and mathematically rigorous, but the results depend on the choice of priors. Different priors can lead to different conclusions, especially when the data are ambiguous or when the likelihoods of different hypotheses are similar. This subjectivity in the choice of priors is sometimes seen as a weakness of Bayesian reasoning, but it can also be seen as a strength because it forces us to be explicit about our assumptions and about the role of prior beliefs in shaping our interpretation of evidence. In scientific practice, the goal is to design experiments and observations that are informative enough to overwhelm the influence of priors, to provide such strong evidence for one hypothesis over others that the posterior probabilities converge regardless of the choice of priors. The cold spot, as it stands, does not provide such overwhelming evidence. It remains ambiguous, and different scientists, with different priors, may reasonably reach different conclusions about its significance. This ambiguity, this openness of interpretation, is part of what makes the cold spot such a fascinating and enduring puzzle. It occupies a liminal space, neither fully explained nor fully inexplicable, neither mundane nor definitively exotic. It invites continued inquiry, continued refinement of models and observations, and continued reflection on the methods and principles by which we seek to understand the universe. In this extended exploration, we have journeyed from the basic observational fact of the cold spot, a colder-than-expected region in the cosmic microwave background, through the detailed physics of the cosmic microwave background itself. The mechanisms by which temperature variations are imprinted and modified, the statistical methods by which anomalies are detected and interpreted, the theoretical frameworks of cosmic inflation and the multiverse, and the specific hypothesis that the cold spot might be evidence of a bubble collision with another universe. At each stage, we have sought to build understanding from first principles, to explain the concepts in terms of physical processes and logical reasoning, and to convey the depth and subtlety of the science involved. We have seen that the cold spot is real, that it has been observed by multiple satellites with consistent results, and that it is statistically unusual, though not impossible, as a random fluctuation. We have seen that there are several possible explanations, including a statistical fluke, a supervoid along the line of sight, and a bubble collision. We have seen that each explanation has strengths and weaknesses, that the evidence does not definitively favor one over the others, and that continued research is needed to resolve the question. We have also seen that the bubble collision hypothesis, while speculative, is not baseless speculation. It arises from well-developed theoretical frameworks, particularly eternal inflation, that are themselves motivated by the need to explain fundamental features of the universe like its uniformity and flatness. The multiverse is a natural, though controversial, consequence of these frameworks, and bubble collisions are a natural, though rare, consequence of the multiverse. If such collisions occur, they would leave observable signatures, and the cold spot is a candidate for such a signature. The significance of the cold spot, therefore, extends beyond the specific question of whether it is evidence for another universe. It exemplifies the way in which cosmology operates at the boundary between the known and the unknown, using observations of the universe to test and refine our theories, and using theories to interpret and guide observations. It illustrates the importance of statistical reasoning, of careful attention to systematic errors and biases, and of openness to multiple hypotheses. And it raises profound questions about the nature of the cosmos, the limits of observation, and the scope of scientific inquiry. As we consider these questions, we are reminded that the universe is vast, far vaster than the scales of everyday experience, and that our understanding of it is necessarily incomplete. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is finite, bounded by the cosmic horizon. Beyond that horizon, there may be more universe, more structure, more complexity, but it is forever hidden from our view, inaccessible to observation, because light from those distant regions has not yet had time to reach us and never will, due to the accelerating expansion of space. The multiverse, if it exists, extends this inaccessibility to a new level. Other universes, other bubbles in the eternal inflating background, are not merely beyond our horizon. They are in principle disconnected from us, separated by regions of exponentially expanding space. We cannot travel to them, we cannot communicate with them, and under normal circumstances, we cannot observe them. The only exception is if such a universe collided with ours in the distant past, leaving an imprint on the cosmic microwave background that we can detect today. The cold spot is one candidate for such an imprint. If the cold spot is indeed evidence of a collision, then it represents an extraordinary opportunity, a rare window into a domain of reality that would otherwise be completely inaccessible. It would be a case where the universe, through a chance event in the distant past, has provided us with information about something beyond the observable universe, something that, by all standard reasoning, should be unobservable. This possibility is what lends the cold spot its profound allure and its importance to fundamental physics. But even if the cold spot is not evidence of a collision, even if it is ultimately explained by more conventional means, it will have served a valuable purpose. It will have motivated theoretical work, refined observational techniques, deepened our understanding of the cosmic microwave background, and reminded us of the need for humility and openness in the face of the unknown. Science does not always provide the dramatic answers we might hope for, but always provides learning, progress, and a deeper engagement with the reality we inhabit. In reflecting on the journey we have taken, we might also consider the human dimension of this inquiry. The cold spot, and the question of whether it is evidence for another universe is not merely an abstract scientific problem, but a reflection of deep human curiosity about our place in the cosmos. For as long as humans have looked up at the sky, we have wondered about what lies beyond the visible, about whether our world is all there is, or whether there are other worlds, other realms of existence. These questions have been explored in mythology, philosophy, and religion for millennia, and now, in the modern era, they have become scientific questions, questions that can be addressed through observation and reason. The possibility of a multiverse, of other universes beyond our own, resonates with these ancient questions. It suggests that our universe, vast as it is, might be just one small part of a far larger structure, and that the principles that govern our universe might be just one realization among many possible realizations. This idea is both humbling and exhilarating. Humbling because it diminishes the cosmic significance of our particular universe, and exhilarating because it expands the scope of reality far beyond what we can directly observe. Yet the pursuit of this idea must remain grounded in empirical evidence and logical reasoning. The multiverse cannot be accepted on faith or on purely aesthetic grounds. It must be tested to the extent possible against observation. The cold spot is one such test. If it is evidence for a bubble collision, then the multiverse moves from being a speculative hypothesis to being an empirically supported framework. If it is not, then we must continue to search for other tests, other ways of probing the limits of the observable universe and the possible existence of a larger cosmos beyond. This search is ongoing. It involves not only the study of the cosmic microwave background, but also many other areas of cosmology and fundamental physics. It involves the search for gravitational waves from the early universe, which could provide information about the energy scales of inflation and potentially about the landscape of possible vacuum states. It involves the study of the distribution of galaxies and the large-scale structure of the universe, which encodes information about the initial conditions and the growth of structure over cosmic time. It involves the study of the properties of dark matter and dark energy, whose nature might be linked to the fundamental structure of space and time and to the possible existence of extra dimensions or other exotic features predicted by string theory and other frameworks. All of these lines of inquiry are interconnected, and progress in one area often illuminates others. The cold spot, as one particular feature in one particular dataset, is just one piece of a much larger puzzle. But it is a particularly intriguing piece, one that has captured the imagination of scientists and the public alike, because of its potential connection to the multiverse and to the possibility of evidence for another universe. As we continue to study the cold spot, as we refine our measurements and our models, as we search for correlated signals and additional collision signatures, we are engaged in a process of exploration that is both deeply empirical and deeply philosophical. We're using the tools of modern science to address questions that touch on the very nature of reality, on the structure of the cosmos, and on the limits of what we can know. This process is slow and painstaking, often frustrating in its ambiguity, but is also immensely rewarding, offering glimpses of a universe far stranger and more complex than our ancestors could have imagined. The cold spot, cold not in any ordinary sense, but in the specific sense of a temperature deficit in the cosmic microwave background, stands as a symbol of this exploration. It is a feature in the data, a pattern of photons arriving at our detectors, carrying information encoded across more than 13 billion years of cosmic history. It is a puzzle that resists easy explanation, that invites multiple hypotheses, and that challenges us to think carefully about the methods and principles by which we interpret the signals the universe sends us. In the end, whether the cold spot is evidence for another universe remains an open question. The answer may come in the form of new observations, new theoretical insights, or new statistical techniques that allow us to discriminate between competing hypotheses with greater confidence. Or the answer may remain elusive, leaving the cold spot as an enduring mystery, a reminder of the limits of our knowledge and the vastness of what remains to be discovered. But the pursuit of the answer, the process of inquiry itself, is valuable regardless of the outcome. It exemplifies the scientific method, the commitment to evidence and reason, the willingness to entertain bold hypotheses while subjecting them to rigorous scrutiny, and the recognition that our understanding of the universe is always provisional, always subject to revision in light of new evidence. It embodies the spirit of exploration that drives cosmology and all of science, the desire to know, to understand, to push the boundaries of the known ever outward. As we stand here, in our particular moment in cosmic history, observing the universe with instruments of unprecedented power and precision, we are participants in a grand endeavor, an endeavor that spans cultures and centuries, that connects us to the earliest stargazers and to the future generations who will build on our discoveries. The cold spot is one chapter in this story, a chapter still being written, and its resolution, whatever form it takes, will add to the ever-growing body of knowledge we have accumulated about the universe. The cold region in the sky, this particular configuration of slightly less energetic photons arriving from a specific direction, may ultimately be explained by a supervoid, a chance fluctuation, a subtle systematic error we have not yet identified, or just possibly by a collision with another universe, another bubble in the inflationary multiverse. Each of these possibilities tells a different story about the cosmos, about the processes that shape it, and about the nature of reality on the largest scales. The supervoid explanation tells a story of large-scale structure, of the cosmic web of galaxies and voids that fills the universe, of the gravitational effects of underdense regions on the propagation of light, and of the integrated Sachs-Wolf effect, a subtle but important modification of the cosmic microwave background by the evolving gravitational potentials of large-scale structure. This story is grounded in well-established physics, in general relativity, and the dynamics of cosmic structure formation, and it requires only that the universe contain a particularly large and deep void along the line of sight to the cold spot. Such voids are rare, but not unprecedented, and their existence is a natural consequence of the growth of structure from small primordial fluctuations. The statistical fluctuation explanation tells a story of quantum origins, of the random fluctuations in the inflaton field during inflation that were stretched to macroscopic scales and became the seeds of cosmic structure. These fluctuations are inherently random, drawn from a probability distribution, and rare events, by definition, occur with low probability but are not impossible. The cold spot, in this story, is simply a rare draw from the distribution, a fluctuation on the tail of the Gaussian distribution that characterizes the primordial perturbations. This explanation requires no new physics, no unusual structures, no exotic processes. It is the simplest explanation in the sense of invoking the fewest additional assumptions, but it is also the least satisfying because it does not provide a physical mechanism, only a statistical description. The bubble collision explanation tells a story of the multiverse, of eternal inflation, of a vast landscape of universes, each with its own properties, and of the rare but possible event of two bubbles colliding. This story invokes physics beyond the standard cosmological model, requiring the framework of eternal inflation and the reality of the multiverse. It is the most exotic of the explanations, the most speculative, but it is also the most profound in its implications. If true, it would confirm that our universe is not alone, that there are other universes, and that, under certain circumstances, those universes can interact in observable ways. It would provide empirical evidence for a theoretical framework that has been developed over decades, but has remained largely untested, and it would open a new window into the fundamental nature of the cosmos. These three stories, and others that might be constructed, are not merely abstract narratives, but are specific, quantitative hypotheses that can be tested, compared, and evaluated in light of the evidence. The process of evaluation is ongoing, and the outcome is not yet determined. Future observations, from next-generation cosmic microwave background experiments, from deeper galaxy surveys, from improved theoretical models and simulations, will gradually constrain the possibilities and move us toward a resolution. But even as we work toward that resolution, we can appreciate the cold spot for what it already is, a remarkable feature in the cosmic microwave background, a challenge to our understanding, a stimulus for research, and a potential signpost pointing toward new physics or toward a deeper understanding of the cosmos. It is a cold region in the sky, but it is also a hot topic in cosmology, a focus of intense study and debate, and a reminder that the universe still holds mysteries that we are only beginning to unravel. In contemplating the cold spot, we are brought face to face with the fundamental questions of cosmology. How did the universe begin? What is its ultimate fate? Is our universe unique, or is it one among many? How large is the cosmos, and what lies beyond the observable horizon? These questions have been asked in different forms throughout human history, but only in the modern era have we developed the tools to address them scientifically through observation and experiment. The cosmic microwave background, with its intricate pattern of temperature fluctuations, is one of the most powerful tools we have for probing the early universe and testing cosmological theories. It is a direct signal from the distant past, from a time when the universe was young and simple, before stars and galaxies had formed, before the complexity of the present-day cosmos had emerged. By studying this signal, we can learn about the conditions in the early universe, about the processes that shaped it, and about the fundamental physics that governs its evolution. The cold spot, as one particular feature in this signal, concentrates our attention on a specific region of space and a specific set of physical processes. It asks us to consider whether the standard model of cosmology, successful as it is complete, or whether there are additional effects, additional structures, or additional physics that must be taken into account. It pushes us to refine our measurements, to improve our models, and to think critically about the interpretation of data and the evaluation of hypotheses. In doing so, the cold spot serves a valuable role in the scientific process. Science does not progress only by confirming predictions and accumulating successes. It also progresses by confronting anomalies, by grappling with unexplained features, and by testing the limits of existing frameworks. Anomalies are often the seeds of revolutions in scientific understanding. They are the places where new ideas emerge, where paradigms shift, and where our picture of the universe is transformed. Whether the cold spot will lead to such a revolution remains to be seen. It is possible that it will be explained within the existing framework as a rare fluctuation or a super void, and that it will recede into the background as just another well-understood feature of the cosmic microwave background. But it is also possible that it will prove to be the first empirical hint of something deeper, something that requires an extension or modification of the standard cosmological model, perhaps in the direction of the multiverse, perhaps in some other direction that we have not yet anticipated. The history of science suggests that both outcomes are possible and that the process of determining which is correct is lengthy and requires sustained effort by many researchers. Major discoveries are rarely the result of a single observation or a single insight. They emerge from the accumulated work of many individuals, from the gradual refinement of theories and measurements, from the interplay of skepticism and openness, and from the willingness to entertain bold ideas while subjecting them to rigorous testing. The cold spot, in this context, is part of an ongoing conversation, a conversation among scientists and between scientists and the universe. It is a feature that the universe has presented to us, and we are responding with questions, with hypotheses, with observations, and with calculations. The universe, in turn, responds through the data it provides, sometimes confirming our expectations, sometimes surprising us, always challenging us to refine our understanding. As we continue this conversation, as we probe the cold spot with ever more sophisticated tools and ever more refined analyses, we are engaging in one of the most profound activities of human culture, the attempt to understand the natural world through reason and evidence. This activity is neither purely objective nor purely subjective. It involves creativity and intuition, discipline and rigor, collaboration and debate. It is a social process conducted within a community of researchers who share common standards and methods, who build on each other's work, who critique and challenge each other, and who collectively advance the frontier of knowledge. The cold spot, as a topic of research, exemplifies this social process. It has been studied by multiple research groups, using data from multiple satellites, employing different statistical techniques and different theoretical models. The results have been published in peer-reviewed journals, presented at conferences, and debated in the scientific literature. Some researchers are more inclined to favor the bubble collision hypothesis, others the supervoid hypothesis, and still others remain agnostic, waiting for more definitive evidence. This diversity of perspectives is healthy and productive. It ensures that all possibilities are explored, that no hypothesis is accepted uncritically, and that the evaluation of evidence is thorough and fair. In the broader public discourse, the cold spot has captured attention because of its potential connection to the multiverse and to the idea of other universes. This connection taps into deep currents of human thought and imagination, into questions about our place in the cosmos and the nature of reality. It resonates with themes in science fiction, philosophy, and theology, and it invites reflection on the limits of human knowledge and the scope of existence. However, it is important to maintain a clear distinction between the scientific investigation of the cold spot and the broader cultural and philosophical reflections it inspires. The scientific investigation is grounded in observation, in testable hypotheses, in statistical analysis, and in the rigorous application of physical theories. The cultural and philosophical reflections are valuable and important, but they operate in a different domain, one that is not constrained by the same requirements of empirical evidence and logical consistency. As scientists, our task is to pursue the investigation with integrity, to follow the evidence wherever it leads, to be open to surprising conclusions, but also to be cautious and critical, to demand high standards of evidence, and to resist the temptation to overinterpret ambiguous data. The cold spot may be evidence for another universe, but it also may not be. Our responsibility is to determine which is the case, or to acknowledge when the evidence is insufficient to decide. This responsibility extends to the communication of science to the public. The cold spot has been the subject of many popular science articles, documentaries, and discussions, and in some of these, the bubble collision hypothesis has been presented as more certain or more likely than the current evidence warrants. While it is natural and appropriate to explore exciting possibilities and to convey the sense of wonder that scientific discoveries can inspire, it is also important to communicate the uncertainties, to explain the alternative hypotheses, and to convey the provisional nature of scientific conclusions. The public's understanding of science is shaped in part by how scientists and science communicators present findings like the cold spot. If we present tentative hypotheses as established facts, we risk eroding trust when those hypotheses are later revised or rejected. If we present science as a body of certainties rather than as a process of inquiry, we misrepresent the nature of scientific knowledge. The cold spot offers an opportunity to communicate science as it actually works, as a process of observation, hypothesis formation, testing, and revision, a process that is often uncertain and ambiguous, but that, over time, converges on a deeper and more accurate understanding of the world. In the case of the cold spot, the process is still unfolding. The observations have been made and confirmed. The anomalies have been identified and characterized. Multiple hypotheses have been proposed. Theoretical models have been developed and tested against the data. But a definitive conclusion has not yet been reached. This is the current state of the science, and it is an honest and accurate reflection of where we are in the investigation. As we move forward, as new data become available, and as theoretical models are refined, the picture will become clearer. We will learn more about the large-scale structure along the line of sight to the cold spot, about the properties of any supervoid that might be present, and about the statistical properties of the cosmic microwave background on large scales. We will develop better tools for testing the bubble collision hypothesis, for simulating what collision signals would look like, and for discriminating between collision signals and other sources of large-scale anomalies. And we will continue to refine our understanding of inflation, of the multiverse, and of the fundamental physics that governs the cosmos on the largest scales. All of this work will take time, and it will require sustained effort by the cosmological community. It will require investment in new observational facilities, in computing resources for simulations and data analysis, and in the training of new researchers who will carry the investigation forward. It will require collaboration across institutions and across national boundaries, because cosmology is a global enterprise, one that draws on the talents and insights of scientists from around the world. The cold spot, then, is not just a scientific puzzle, but also a focal point for a community of researchers, a common challenge that brings together different expertise, different perspectives, and different approaches. It is a reminder of the collaborative nature of modern science, of the way in which complex problems are tackled not by isolated individuals, but by communities working together, sharing data, sharing ideas, and building on each other's contributions. In reflecting on this collaborative process, we might also consider the role of technology in enabling modern cosmology. The detection and characterization of the cold spot would not have been possible without the sophisticated satellites that have been launched to study the cosmic microwave background, without the sensitive detectors and precise calibration techniques that allow us to measure tiny temperature differences, without the powerful computers that process and analyze vast amounts of data, and without the theoretical frameworks and computational tools that allow us to model the universe and compare predictions with observations. Each of these technological capabilities is the result of decades of development, of incremental improvements in engineering, in material science, in electronics, in data analysis algorithms, and in theoretical methods. The cosmic microwave background missions COBE, WMAP, and Planck represent the culmination of long-term efforts by large teams of scientists and engineers, working together to design, build, launch, and operate these complex instruments and to extract the maximum scientific value from the data that they collect. The success of these missions has been remarkable. They have transformed our understanding of the universe, providing precise measurements of cosmological parameters, revealing the detailed structure of the primordial fluctuations, detecting the signatures of cosmic inflation, and uncovering anomalies like the cold spot that challenge our theoretical frameworks. They have also set the stage for future missions, which will build on this success to probe even deeper into the nature of the cosmos. The future of cosmic microwave background research is bright. Next-generation experiments will have higher sensitivity, higher resolution, and the ability to measure polarization with greater precision. They will be able to detect the faint signature of primordial gravitational waves, if they exist, which would provide a direct probe of the energy scale of inflation and would open a new window into the earliest moments of the universe. They will be able to map the large-scale structure with greater accuracy, improving our understanding of the distribution of matter and energy and the processes that govern cosmic evolution. And they will be able to search for additional signatures of exotic phenomena, including bubble collisions, cosmic strings, and other relics of the early universe. These future observations will provide crucial tests of the cold spot hypotheses. They will allow us to map the region in greater detail, to search for correlated signals in polarization and other observables, and to compare the observed features with the predictions of different theoretical models. They will also provide a larger statistical sample, allowing us to search for other potential collision signatures elsewhere in the sky and to assess the frequency of such features. In addition to observational advances, theoretical progress will also be essential. The development of more detailed models of bubble collisions, incorporating the full complexity of the collision dynamics and the propagation of signals through the early universe, will allow for more precise predictions and more stringent tests. The exploration of alternative explanations, including variations on the supervoid hypothesis, modifications to the inflationary model, and other sources of large-scale anomalies, will ensure that all possibilities are considered and that the interpretation of the data is robust. Computational advances will also play a key role. Simulating the universe, from the earliest moments after the Big Bang through the formation of the cosmic microwave background and the growth of large-scale structure, requires enormous computational resources. As computers become more powerful and as simulation algorithms become more sophisticated, we will be able to model the universe with greater fidelity, to explore a wider range of scenarios, and to make more accurate predictions for comparison with observations. All of these advances, observational, theoretical, and computational, will contribute to the resolution of the cold spot puzzle and to the broader effort to understand the universe on the largest scales. They will move us closer to answering the fundamental questions of cosmology and to determining whether the cold spot is indeed evidence for another universe or whether it has a more conventional explanation. But even as we look forward to these advances, we can appreciate the current state of knowledge and the journey we have taken to reach it. The cold spot, this cold region in the cosmic microwave background, has led us on a deep exploration of the cosmos, from the basic physics of radiation and temperature, through the history of the universe from the Big Bang to the present, to the frontiers of theoretical physics and the speculative but scientifically grounded idea of the multiverse. It has challenged us to think carefully about observation and inference, about the nature of evidence, and about the limits of what we can know. The cold spot stands as a monument to human curiosity and to the power of the scientific method. It is a feature in the data, a pattern in the ancient light that fills the universe, and it has become a focus of intense study and debate. It may be a window into another universe, or it may be a rare but mundane fluctuation, or it may be the result of a large void in the cosmic structure. Whatever its ultimate explanation, it has enriched our understanding and has pushed us to explore new ideas and new possibilities. As this exploration continues, as we gather more data and refine our models, we will gradually converge on an answer. That answer, when it comes, will be the product of careful observation, rigorous analysis, and thoughtful interpretation. It will be grounded in evidence and reason, and it will represent a genuine addition to human knowledge. Whether the answer confirms the bubble collision hypothesis or favors a more conventional explanation, it will be a scientific achievement, a testament to the power of systematic inquiry and to the human capacity to understand the natural world. The cold spot, in the end, is more than just a scientific puzzle. It is a reminder of the vastness of the universe, of the deep mysteries that still surround us, and of the ongoing quest to unravel those mysteries through observation and thought. It is a feature in the sky, a cold region in the cosmic microwave background, but it is also a symbol of the scientific enterprise, of the relentless pursuit of knowledge, and of the wonder that drives us to look outward, to ask questions, and to seek answers. In the quiet of a clear night, when we look up at the stars, we are looking back in time, seeing light that has traveled across vast distances to reach us. The cosmic microwave background, though invisible to our eyes, surrounds us, a faint glow from the distant past, from the moment when the universe became transparent and light could travel freely. Within that glow, in a particular direction in the sky, there is a region that is slightly colder than the rest, a cold spot that has captured our attention and sparked our imagination. It is a small anomaly in a vast cosmos, but it is an anomaly that could hold the key to understanding something profound about the nature of reality, about the structure of the universe, and about the possibility that our universe is not alone. And so the investigation continues, driven by curiosity, by the desire to know, and by the recognition that the universe, in its complexity and its beauty, still has much to teach us. The cold spot remains cold and enigmatic, a challenge and an invitation, a feature in the cosmic microwave background that may or may not be evidence of another universe, but that in either case has deepened our engagement with the cosmos and enriched our understanding of the place we occupy within it. The cold persists, patient and indifferent, encoded in photons that have journeyed across billions of years, carrying information we are only beginning to decipher. It is a coldness measured not by thermometers, but by the spectral signature of ancient light, a coldness that speaks of density, of gravity, of quantum fluctuations, or perhaps of a collision that occurred long before our world existed, before a galaxy formed, before the first stars ignited. It is a coldness that, in its subtle deviation from expectation, has opened a space for wonder and for inquiry, a space where science and imagination meet, where observation grounds speculation, and where the pursuit of understanding continues, patient and relentless, in the face of uncertainty and the vastness of the unknown.